Hello, everybody out there in Math 150. We're looking at our last objective for section 3.4, and that's finding horizontal and oblique asymptotes. Now, you may remember from our last video that in vertical asymptotes, we can never touch them, and our function is forced to go to infinity or to negative infinity. So our function is going to be going all the way up or all the way down somewhere in the middle of the graph. We're going to start off today by looking at horizontal asymptotes, and the idea of a horizontal asymptote is the following. This should kind of make sense to you. It is going to be a horizontal line that the graph is going to have that the function is going to get closer and closer and closer to. So one path the function might take to get to the horizontal asymptote is this, okay? And again, it's the idea of having that magnet at the end, just drawing the function over, okay? So that's one path we might have, okay? Another path it might take is this one, a little different, but along the same lines. Maybe it goes up and then comes back down and heads towards that value, okay? Now, here is the difference between horizontal and vertical asymptotes. You can cross horizontal asymptotes. Let me say that again. You can cross a horizontal asymptote. It's perfectly legit to cross the horizontal asymptote. You can never cross a vertical asymptote. Vertical asymptotes come from domain problems. You can't cross a domain problem. So that's why you can't cross the vertical. The horizontal asymptotes can be crossed. Here is another way this function could look, okay? It could look like coming from the top and just going down. So any of these three functions would be a drawing using a horizontal asymptote. Now, the other thing to keep in mind is you can also have a horizontal asymptote that's going in the other direction. So let's back these up a little bit. Back these up a little bit. What if I now said, okay, this guy comes up and then does this? Well, that's like saying, okay, now we've got the magnet over on this end, and it's drawing the function over as well. Likewise, this orange graph could use this horizontal asymptote and come right back up. And the blue graph could do the same thing and start headed towards the horizontal asymptote as well. So what is the deal with horizontal asymptotes when you're trying to find them? Simple. We're trying to find the y value as the x value goes all the way, and that's important, goes all the way to the right, or the left. Now, all the way to the right, when we say all the way to the right, all the way to the right means as x goes to infinity. Okay, all the way to the right, the biggest values you got, all the way at the end of the line, x is going to infinity. All the way to the left means as x goes to negative infinity. And the y values, what that means is f of x. So if you break this down, find f of x, find the y values, and I forgot to put the word as there, find the y value as the x value, go all the way to the right or left. So find the y values, find the function values as x goes to infinity or negative infinity. So here's how we're going to write these problems. Okay, we're going to start with this g of x example right here. We're going to use this guy, we're going to move down a little bit, and we're going to say find the horizontal asymptotes. So find the horizontal asymptotes for g of x. So the way we would write that is we would ask, what does 1 over x do? And I like to write it like this, as x goes to infinity. What does 1 over x do as x goes to negative infinity? So in other words, we're just saying, if we plug in bigger and bigger numbers, what do the outputs get closer and closer to? Okay. Now, the way I like to think of this, I like to think of a story that I tell my students, okay? Let's say I'm hungry and I want to have a pizza. So I'm starving, I'm going to eat my pizza. And I'm all excited to eat it. I've got the whole pizza to myself. But as I'm about to start to eat, one of my students walks in and they're hungry too. So now I have to share. So now I'm going to have one pizza divided by 2 people. That's going to get me half a pizza. Well, if more people come in, if 2 more students come in, I'm now going to have to share it with 4 total people. I'm going to get a 4th pizza. If 10 people come in, I'll get a 10th of a pizza. If 100 students happen to come in, I'll get 1/100th of a pizza. As the X values go up, the outputs go down. So we come up with this rule that says if you divide by more, you're going to get less. So that's kind of the key on this one, right? If we divide by more, we're going to get less. Well, if we divide by the most, that means we're going to get the least. Well, the most we can divide by is some kind of infinite value. That's either infinity, positive infinity, or negative infinity. We're going to end up with the least value. The least value is 0. Think about that pizza again. If I had to divide it with 1,000 people, how much pizza would I get? A really small piece. What if I divide it with by 1,000,000 people? Or crazy talk. What if I divide it by 1,000,000,000 people? If you could possibly cut a pizza into 1,000,000,000 slices, the slice would be microscopic. So we're talking about the value is getting closer and closer and closer to 0. What that means in this example up here, we're dividing by more, we're going to get less. These are both going to 0. So when we think about the graph of 1 over x, that means we have a horizontal asymptote at y equals 0. We're going to get that from these two values here. So as we go to the left, all the way to the left, we're going to get y equals 0. That's what this guy is saying. And as we go all the way to the right, we're going to get y equals 0 again. That's what this guy is saying. So now think of it as there's magnets out there. The way this graph is going to look is it's going to get closer and closer and closer to those horizontal asymptotes. So that's the idea. The idea is this, basic premise. To find horizontal asymptotes, do the function as x goes to infinity, and do the function as x goes to negative infinity. So I'm going to talk to you about how to compute what happens when we go to infinity and negative infinity. But the first thing you saw is if you're dividing in the bottom is getting bigger and the top is staying constant, this guy's going to go to 0. Okay? So keep that in mind. We're going to take a couple more examples. So now in this example, here's what's happening. I've got 3x on the top and x minus plus 4 on the bottom. If I think about this going, or what this is doing as x goes to infinity, well, most people are going to say the top's going to get bigger and the bottom's going to get bigger. Problem is, infinity is not a number, so I don't know how to handle that. Infinity divided by infinity might not be 1. It could be anything. So we got to think about this for a second. So I'm going to encourage you to just use a little bit of common sense here. Think about this in terms of how much, let's say, money you had, okay? So if we're talking about money, if I've got a value that's increasing, right, x is getting large. So if I have $10 and I add 4 to it, I have 14, right? So that 4 is kind of nice, adds to the 10. If I have $100 and I add 4 to it, okay, still pretty good. I've got more money. I'm going to go from 100 to 104. But as this number gets bigger, think about what the 4 means to it. $1,000 and you have a chance to get 4 more. Well, depends on what I have to do to get the $4. What if I had $1 million and they told you get $4 more by doing something you didn't really want to do? Would you do it? You might not because you have $1 million. And now let's think about if you're Jeff Bezos, right? Founder of Amazon. He's got billions of dollars. If you had $100 billion and someone said, oh, I'm going to add 4 more to you, all of a sudden that 4 doesn't seem all that important. We're talking about something that I call significant and insignificant terms, okay? The significant term is the term with the highest exponent. Okay? The significant term is the term with the highest exponent. The other terms are insignificant. So when I look at this problem again, when I look at 3x over 4 plus x, and because x is going to infinity, the 4 is going to lose importance. What I say is this is going to behave like 3x on the top, and it's going to behave like x on the bottom. Because as x gets larger and larger, the 4 matters less and less. Because of that, we're going to get an answer of 3 here. So this means that we have a horizontal asymptote at y equals 3. That would be our answer. That's on the right side because we're going to infinity. You would then look on the left side, and you would do the exact same thing. But as x goes to negative infinity, no surprise, again, that 4 is not significant at all. So this is again is going to behave like 3x over x, and we're going to get 3 on the left-hand side. So again, we're going to find a horizontal asymptote at y equals 3. When you go to graph this guy, what this graph is going to do, and we're not going to make a perfect graph, but what we know is at the value of 3, we have a horizontal asymptote going to infinity and going to negative infinity. So we know our graph is going to get drawn to these values. So it might do something like this. It might start down here and get close to it like that. Or maybe it will come from above. Maybe we'll even overshoot it and then come back down. But we know as we go this way, it's going to get closer and closer to this asymptote. Same thing on the other side. It might look like this. It could look like this. It might overshoot it and come back down. But as we get over to the far left, the function is going to be somewhere really, really close to this line. So those are 2 examples of horizontal asymptotes. We're going to look at one more. We're going to look at this one. And we're going to ask what happens when 2x cubed minus x squared minus x over x squared plus 1, what happens as x goes to infinity? Well, again, we're going to talk about the significant terms, okay? And the significant term is the term that has the greatest exponent. So all of a sudden, this is the significant term at the top, and this is the significant term on the bottom. Our function is going to behave like the significant terms behave compared to each other. So the other ones are insignificant and literally means you can ignore it, but only when we're going to infinity as we are in this problem. That's going to give us 2x when we reduce. Well, now if you ask what happens to 2x as x goes to infinity, it's going to go to infinity. If we look at this exact same problem, as x goes to negative infinity, the significant terms will stay the same. So it's going to behave again like 2x, but now we're asking as x goes to negative infinity. Well, this time we're going to get negative infinity. So graphically, what we're talking about in this problem is we are talking about on the far right side, as x goes to infinity, the y value is going to infinity. That means our function's headed in that direction. It's going up in that top corner. This says as the function, as x is going to negative infinity, we're going all the way to the left, the outputs, the y values are going all the way down. This tells me we're going to end up down there. So we've got an idea now of how these graphs are going to look based on what they're, and this is also called end behavior, how their horizontal aspects or their end behavior on the right end or on the left end, how they're going to behave. So I want to summarize this for you guys. The way we're going to summarize it is this. If you have a polynomial, okay, or I should say a rational function, you've got a nice rational function where the polynomial on top is am x to the m plus am minus 1 x to the m minus 1 plus dot, dot, dot. You remember this from our polynomial definition. And you've got a function on the bottom that is an x to the n plus an minus 1 x to the n minus 1 plus dot, dot, dot. All we care about are the significant ones. And the significant ones are going to be the leading ones if we write it in the right order. So these are always going to behave like the coefficient of the leading term with that exponent on the numerator and the coefficient of the exponent on the denominator. Well, here's the deal. If m equals n, we're going to get a situation like this. We're going to get a situation, something like maybe 5x cubed over 2x cubed, right? The exponents are the same. So if we take it down to that, what that means is we're going to end up with just the coefficients. So we're going to see y equals, in this case, 5 halves, but in general, the coefficient of the top divided by the coefficient of the bottom. And that's going to be your answer if m equals n, okay? If m is greater than n, in other words, the top is greater than the bottom, that means you're not going to have a horizontal asymptote. So no horizontal asymptote, because your function is going to go to either infinity or negative infinity. So that's that situation where we're going to be pointing to one of the corners, okay? So again, that's if the top is greater than the bottom. And then if n is greater than m, in other words, the bottom is greater than the top, all right? In that situation, we're going to have a problem where we're going to end up with something like the first example, where the top is not going to be able to keep up with the bottom. And this means that our function is going to have a horizontal asymptote, and it's going to be at y equals 0. Okay, it's going to be at y equals 0. I'd love to go through and show a couple of examples with you guys to show this. We're going to find the leading terms, we're going to find the highest exponents, and we're going to see how that plays out. So if you guys will follow me along down to these examples. In example 1, it's 3x over x. And as x goes to infinity, that's going to give me 3. So our horizontal asymptote is y equals 3. This is the case where the top and the bottom are the same, because we've got a degree of 1 on the top and a degree of 1 on the bottom. So you just put the significant terms on top of each other. In problem number 2, it's going to be 2x over 5x squared. When you've got 2x over 5x squared, that's the same as saying, if I reduce this, 2 over 5x, and you can see that the bottom is going to get bigger and bigger and bigger, so this thing is actually going to go to 0. So y equals 0 is your horizontal asymptote. Okay? So if they're equal, you make the fraction and you take the ratio of the numbers. If the bottom is bigger, it ends up going to 0. When we go to the next one, the biggest value exponent on the top is 3x squared. On the bottom, it's negative 5x squared. Include the sign. So this is going to act like 3x squared over negative 5x squared. Well, because the exponents are equal, the answer is going to be the ratio of those coefficients. So we're going to get negative 3/5 as our result, and that means y equals negative 3/5 is our horizontal asymptote. So when they're equal, you just take the coefficients. When you go to the next one, we're going to see that x to the 5th is the highest on the bottom and x to the 3rd is the highest on top. This is going to behave like x to the 5th over 4x to the 3rd. If you reduce that, you're going to get x squared over 4. Well, as x goes to infinity on this one, this guy's just going to keep going up. It's going to keep going to infinity. So there is no horizontal asymptote on this. It would be pointing up in the right corner instead. When we go to the next one, we're seeing that the bottom is bigger than the top. The 10 on the bottom, the exponent is bigger than the 4 exponent on the top. This is a case where the bottom exponent is larger. Anytime the bottom exponent is larger, you're going to get y equals 0 for the asymptote, okay? So if the bottom exponent is larger than the top exponent, y equals 0. If you want to see that in action, significant terms ends up reducing to 1 over 2x to the 6th. And now you can see as x goes to infinity, this thing is going to go to 0 because we're dividing by more and more. One more example. The top is bigger than the bottom in this case. Anytime the top is bigger than the bottom, no horizontal asymptote. This is going to behave like x, and as x goes to infinity, this will go to infinity. So no horizontal asymptote. So just to review really quickly, if the degree on the top is equal to the degree on the bottom, you use the two coefficients as a ratio. If the degree on the top is less than the degree on the bottom, in other words, it's bigger on the bottom, your asymptote is going to be y equals 0 every time. And if your degree on the top is greater than the degree on the bottom, in other words, it's bigger on the top, you're going to get an infinite result when you're trying to the asymptotes. That means you're going to go off to infinity in the top left corner or the top right corner, or you're going to go down to negative infinity in the bottom left corner or the bottom right corner, depending on if you get infinity or negative infinity. I hope that makes sense. There's plenty of practice problems on this. If you have any more questions, please feel free to reach out to me. We're going to be coming back with one last short video to explore what happens when there's no asymptote again. In other words, what happens when the top is greater than the bottom. Tune in next time when we take a look at that, okay? And that's where the oblique asymptotes will come in. Have a great day, everybody.